Okay, good. Can you see my screen? Oh no, I can't see my screen. Uh-huh. 1 second. Take it off and then put it back on again. Hopefully this will solve the problem. Yes. Okay, so now it's being recorded. Okay, so again, I'm sorry that I've forgot to record. This is just for the reference, so it will be in the recording thing. Okay, so now we said that O prime is moving with respect to O in the X direction. So what does it mean? It means that by definition, X prime is not the same as X, but Y prime is Y and Z prime is Z. So from these equations, right, we must have that T prime is not equal to T, which is quite straightforward. So the inevitable conclusion that we have here is that time separation is not the same in both frames. Okay. So far, everything that I said is something which I believe that you've seen, right? There's nothing that you haven't seen. Good. Now, in math language, we say that this is not invariant quantity. So this is not an invariant quantity. But there is a quantity which is invariant. And what is that? Invariant
Speed of
means
light.
the speed of light is constant of nature. Yes, but there is another quantity which is invariant. Invariant means it is not changed under when I'm changing from one the interval, right? So there is a quantity which we define as an interval. And that's the interval between two events. And invariant means that invariant, right? Invariant means that two different observers, which are located in two different inertial frames, agree on that quantity. Okay, so yeah, so speed of light obviously is constant, is invariant, right? But also what's called the interval between two events. Which is defined as interval squared and is also called delta S squared. The delta is because it's between two events, is defined as minus C delta T squared plus delta R squared, which is minus C delta T squared plus delta X squared plus delta Y squared plus delta Z squared. So again, delta T is the time separation between the two events. So in our case here, in the example here, right, the first event is the emission of photon, and the second event is that the photon reach here or the detection of the photon. Right. So this is the second event. And the interval is the time separation between these two events minus the space separation between these two events. And this is an invariant quantity. So both observers, of course, in this case, it will be a zero, because we're talking about a photon. Both observers would agree on the interval between the two events. Although they disagree in general on the time separation between the two events, they disagree in general on the space separation, they do agree on the interval. And there is a classical analogy. Questions about that? No? Okay. So there is a classical analogy, and the classical analogy, of course, is the distance in Euclidean space. So this is an analogy. Distance in Euclidean space. Let's do 2-dimension, 3-dimension. It doesn't matter. You're familiar with that. So if I take a 2-dimensional space, x, y, and I set 2 points, right? I can look at the distance between the 2 points. Which is delta s, right? And the distance between the 2 points, delta s squared, of course, is delta x squared plus delta y squared, right? This is x1, x2, y1, and y2, right? Delta x is x2 minus x1 squared plus y2 minus y1 squared, right? Now, if there is another coordinate system which is rotated with respect to the first coordinate system, so let's take another coordinate system. X prime and y prime. Right, so in this new coordinate system, these are the values of the points, x1 prime, x2 prime, and this would be y1 prime, y2 prime. So obviously, delta x is not the same as delta x prime. Delta y is not the same as delta y prime, but delta x prime squared plus delta y prime squared is delta s prime squared is equal to delta s squared. So in Euclidean geometry, right, distance in Euclidean geometry is invariant when I'm rotating the coordinate system. Okay? Again, there's nothing surprising. I mean, I'm not saying anything that is you don't know already. Okay? Again, for those of you who don't open the cameras, I'll be happy if you could open your cameras. And in general, I do want you, if there is something that I say that you don't understand, please stop me. Okay, there is no such thing as stupid questions. Certainly not.
I have
Yes.
a question.
Yeah.
But we already know that the distance in if observer O prime is moving near speed of light, we already know that the distance is not the same. The delta x is not the same for both systems.
Doesn't matter.
It doesn't matter.
Of course, it's not the same. The distance is not conserved, right? It's not invariant, but the interval is the same.
Okay, thank you.
You'll see that.
Thank
It will fall out. Okay. So we say that the distance in Euclidean space, we say that the distance is invariant under rotation of the coordinate system.
There's a question in the chat.
Just a second. I don't see the chat, so please read it to me because I can't see the chat and share my screen at the same time.
Why is there a minus sign on the CT in the interval?
Why is there a minus sign?
Yes, that's the question.
Because if you look at these equations here, right, I have to move them to the other side. Right? If I don't move them to the other side, then I get a mess. That's why it's a minus sign.
Thanks.
Okay. Okay. Having that, now we can start. Having that as basic definitions, now we can start. And we're going to start by talking about Lorentz transformation. One thing which you've already seen, which is actually directly related to the question of this minus sign, right, is that this interval, which I just introduced, interval here, what it does, it connects the space and time into one four-dimensional space-time. Because the interval is conserved, I can no longer think of space and time to be completely separate things, as I'm used to in Newtonian physics. Okay? I should write it down because that's an important point. The interval connects space and time into a 4D space-time known. You've heard the name. What's the name of that?
Minkowski.
Yeah, this is called Minkowski space. So in that Minkowski space, one can define an event by its time and space coordinates. So we need total of 4 coordinates to define an event. An event is defined by its time and space coordinates. You know, T, X, Y, Z. So there are total 4 quantities required to completely specify an event. Okay. Now we're going to start introducing notations. So rather than working with T, X, Y, Z, we're going to use the vectorial notation with an upper index. So it's quite common, and that's the next thing that you should know already. We're going to make use of most of the Greek alphabet in this course. So you can refresh your memory with the Greek alphabet. So rather, so it is convenient to denote coordinates in 4D space, space-time, by Greek letters or Greek superscript. Superscript, which runs from 0 to 3. In very, 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 very old textbooks, you could find that it goes from 1 to 4, but for many years now, nobody is making use of that. So it's always from 0 to 3. Which means that any event is defined or determined. Defined is good by a 4 vector of coordinates. Call it x mu. It's an upper index. It's important, such that x0 is really ct, x1 is x, x2 is y, and x3 is z. And overall, we call it x mu. That's a convention. It's a language we use. Now, if we only refer, that's another convention, if we only talk about space coordinates, so we don't have the time, then it's common to use the Latin indices. So if we refer only to space, we use Latin indices. We use the Latin indices. xi, so x1 is x, x2 is y, x3 is z. If you're saying I, j, k, Latin indices, that means we're only referring to the spatial coordinates. The only place in this course that this will be relevant is when we speak about cosmology. We'll see. Generally, we're going to make use of these 4 coordinates, time x, y, z. So we're going to use Greek letters. X mu, x nu, x rho, x sigma. We're going to make use of most of the Greek alphabet here. You'll see that. Okay, so this is the casting. Another notation which is quite convenient for us is to introduce a 4x4 matrix. So we introduce a 4x4 matrix which has a name. It's called a metric. We introduce 4x4 matrix, which we call the metric. And this matrix we're going to write with 2 lower indices. So we're going to call it eta, and it's going to contain 2 lower indices, mu and nu. And it's a very simple matrix. It's zeros outside of the diagonal, and on the diagonal it's going to be a -1, +1, +1, and +1. And everything else is 0. That's a 4x4 matrix. Very simple one. For those of you who took the not quantum field theory, but the particle physics course last semester, and also for those of you who will take or planning to take quantum field theory course. So the same matrix appear in the quantum field theory in particle physics, but in a reverse sign. So eta QFT is a minus eta GR, or astrophysics, which is +1, -1, -1, -1, and the rest are 0. This is for your knowledge. This is a convention. Again, there can be various reasons for that, most likely historical reasons. And of course, the important reason to confuse the students and to make particle physics community unable to talk to astrophysical community in a simple way. Okay, so just that you know, this is a course in general relativity, so we're going to use this formulation here, right? The one that is standard. You will find it in all textbooks of general relativity, no exception. Okay. Now, with this new notation, we're going to write the interval in a compact way, in a compact form, right? So delta S squared, right? Remember, we introduced the interval delta S squared was a minus C squared delta T squared plus delta X squared plus delta Y squared plus delta Z squared. So now I'm going to write down the same interval as a sum over mu and nu from 0 to 3 of what? Eta mu nu, that takes care of the sign, right? Times delta x mu, delta x nu. Okay, take a few seconds and realize that what is written here is exactly what is written here, right? This is exactly what is written here. Now is that clear to everybody? Yeah, guys. Is that clear to everybody?
Yes.
Yes.
Okay, good. In that case, we're not going to need the summation, so I'm just going to write it without the summation. So this is equal to eta mu nu delta x mu delta x nu. So what I did was using something which is called Einstein summation convention. And the Einstein summation convention tell us that when we have an equation that on the same side of the equation we're seeing the same index, so the same Greek letter that appears twice, once as an upper index, once as a lower index, we understand that really we are summing over this index. Okay? Indices that appear both as subscripts and superscripts on the same side of an equation are summed over. Okay, if that confuses you, you simply add up summation here over mu and u. Okay, these indices, by the way, are called dummy indices, from reasons which will become clear shortly. The same Greek letter cannot appear more than twice on the same side of an equation. Once as an upper and once as a lower. If it appears more than twice on the same side, or it appears twice both uppers or both lowers, that means that you wrote the equation in the wrong way, so you have a mistake. Okay? That's what it means. Good? Again, of course, the main idea is to confuse the poor student that tries to understand what's going on here. Yes.
Can you explain why the lower index is considered as contravariant and the upper is invariant?
We will get to that.
Okay.
Don't worry. Everything is going to be clear. I'm not sure if today, but by the end of next week, it will be very clear. Okay, so don't worry about that. We will get there. Of course, once you get used to it, it gets pretty much automatic. You barely need to think. It's just you see right away when it's written properly. So from here on, that's what I'm going to use, right? Now with that new notation, I can define the Lorentz transformation. So what is a Lorentz transformation? There's really very little that I can do. What will be my definition of a Lorentz transformation?
The mathematical, the formula, or the
Physical formula.
physical formula? 1 over the square root of 1 minus c
That's a
u squared
mathematical.
over c squared.
No, that's mathematical. Physically, what is a Lorentz transformation?
The Lorentz transformation, I guess it gives a transformation between perspectives.
In what?
Between observers going at different velocities.
No.
Transform.
Just use terms. You can use terms only terms that we've already talked about in this lecture.
Transforms that conserve the interval.
Yes. Transform between what and what? Two inertial frames, right?
Mhm.
Or two coordinate systems. That conserves the interval. That's all. Lorentz transformation is defined as a transformation from one coordinate system to another that conserves the interval. That's the important point. Well done for saying that. So the first example of such a transformation, of course, is simply a translation, right? So example. One is called here. One is translation. What is a translation? It's just a shift of the origin, right? Shift of the origin by some constant. So what do I mean? X mu is shifted to X mu prime, which is equal to X mu plus some constant A mu. This is some fixed number. Just one comment. Comment about the notation. Note that I wrote down X mu prime. I didn't write X prime mu. Right? Because X mu prime, right? Say like if mu is equal to 2, for example, not this one, right? Because X2 prime is Y. Okay, so comment on the notation. right? So I put the prime over the x mu. Okay, it can be slightly confusing at the beginning, but again, after you get used to it, you see that there is nothing more natural. Okay, so this is one transformation. The only other kind is of a linear transformation. So is what else can we do? Just to multiply the 4 vector x mu with some matrix. Multiply the 4 vector x mu by the space-time invariant. I don't want it to change. Or by 4 matrix. I'm going to write it down as x mu prime. Now I'm going to write down the matrix. Pay attention. So it's going to be a lambda. How am I going to write it? So I'm going to have a one upper index and one lower index so that I can use the Einstein summation convention. So and mu prime and nu, and there is a space. They're not one on top of the other. They come in diagonal. Okay. So do it for now. It will get clear exactly why I'm doing that in the not so distant future. And of course, times x nu. So for example, right, so I can write it down again. Remember, there is a summation here. Summation over what?
Over nu.
Over nu. Right. So really, this is equal x mu prime is equal lambda mu prime 0 x0 plus lambda mu prime 1 x1 plus lambda mu prime 2 x2 plus lambda mu prime 3 x3. This is really what's written here. Right. It's a very compact way of writing somewhat more lengthy equation. Of course, I can also write x prime is just equal lambda x, but this is not common. We won't really find that. Okay, and I said that I wanted to be conserving the interval. So the matrix lambda need to conserve the interval. What does it mean? So in the primed frame, delta S primed squared, right? Everything is working in the primed frame, right? So what is it equal to? What is the interval in the primed frame? How do you write it down?
The metric
The metric eta
mu
what?
mu prime
Prime multiplied by multiplying. Multiplying what?
Delta x mu tag
Delta x mu prime and
delta x nu tag nu
delta
prime.
x mu prime. Right, now delta x mu prime, I can write it down as transformed of the unprimed coordinate. So this is eta mu prime, right? And delta x mu prime is a lambda mu prime mu delta x mu, right? Mu and mu prime are not the same indices, so I can do that, right? Oh, sorry. You know what? I should not do that. Sorry. I don't want it to just be confusing. My mistake. So rho, and then lambda nu prime sigma delta x sigma. Right? Then this needs to be, so I demand it. So I put a quotation mark, right, to make sure that this I demand it to be equal to eta rho sigma delta x rho delta x sigma, which is the interval squared as written in the unprimed frame. So, okay, again, so I'll just mark it down that, this rho and the sigmas, these are really dummy indices. Okay? So these are indices that are summing over. Now, note that when we speak about lambda mu prime rho, right, we're talking about the term in the lambda matrix. So really, we're multiplying term by term, so there's no problem in changing orders. Okay. So the requirement for interval conservation, the requirement that the interval is conserved right, is fulfilled if the elements of the matrix lambda fulfill 1L here, right? What do we have here? Eta rho sigma is equal lambda mu prime rho, lambda mu prime sigma, eta mu prime. So I'm claiming that every matrix lambda whose elements fulfill this equation is a legitimate Lorentz transformation. Any matrix lambda whose components, whose elements fulfill this is a legitimate Lorentz transformation. The set of all these form a group in group theory, if you're familiar with, and this is called, surprise, surprise, Lorentz group. Set of them is called Lorentz group. Okay? Now there are certain categories of Lorentz transformation. So the first category is simply called rotations. Rotations. So for example, if you write down the rotation in the XY plane How does it look like? Rotation around Z. Lambda mu prime nu rotations. How do you write the rotation matrix? In case you get lost, right? T, X, Y, Z. T, X, Y, Z. We're talking about rotation in the XY plane. So how do you write the rotation matrix in the XY plane? Come on, guys. You know the answer to that.
Top line is there 1 0 0 like zeros. Then first column also. Then sinus sorry cosine
Cosine theta, correct.
Sinus theta sinus
Sine theta,
theta
minus sine theta, and cosine theta. That's what you meant.
And then the rest is 0 0 like the columns again 0 and 1 it is
One. Exactly. You've all seen that. Right? This is a rotation of the X and Y axis. Right? And I argue that this rotation matrix is a legitimate Lorentz transformation. Now you can see. In order to see, you need to check. By the way, speaking of, look at that. How many equations are written here?
16.
16, right? Because rho and sigma, each one goes from 0 to 3. So there are 16 equations. And each equation, how many terms in the right-hand side does it contain? How many terms do you have in the right-hand side of each of the 16 equations?
4.
No, why 4?
One for each index. No, it will be more.
So how many?
32. No, it's too much, right?
How many? Well, let's see. We have a summation here over what?
Mu prime, mu prime.
U prime and U prime. So how many total terms there are in the right-hand side of each of the equations?
16, yeah.
16, right? So we have 16 equations, and each one contains 16 terms. Right? So it's very easy, if you're not familiar with that, you can look at that and say, oh, whoa. It's a very compact form, but really it hides behind it many, many terms. Now, because of the simple structure of the eta matrix, which is mostly zeros, then most of these terms are 0. So we don't really care. But if you ask the computer, for example, to give it to answer to, you have to put it 16, right? Of course, when this was written, it was way before people imagined electronic computers. People actually had to do it. Plus, what you're going to see that when we get to general relativity, this is special relativity. When we get to general relativity, the matrix are going to get a much more complicated shape, but one step at a time. Right now, we're talking about that. Okay? So for example, right? So we said, I argue that this here is a legitimate Lorentz transformation. So in order to really check that, you have to write down these 16 equations and see that it fulfills all these equations here. I won't do that, but I can select, for example, if we select rho equals sigma equal to 1, then we have eta 1, 1. What is eta 1, 1? Remember the matrix eta, the metric?
-1.
No,
1.
it's a +1, right? This is the matrix eta, right? So again, t, x, y, z, t, x, y, z, or if you want 0, 1, 2, 3, 0, 1, 2, 3, right? So eta 1, 1 is a +1. So it's a +1 is equal to what? Lambda, what did you say? Mu prime 1, lambda nu prime 1, eta mu prime nu prime. So if you're looking at, let's see, if mu prime, first of all, because of the eta mu prime, right? It's 0 if it's off diagonal. So mu prime has to be equal to nu prime, otherwise everything else is 0, so we don't care, right? So what happens if mu prime is equal to nu prime equal to 0? What is lambda 0, 1? What is lambda 0, 1?
0.
0.
0, right? So we don't care about that either. So the only non-zero terms we have would be lambda 1, 1, lambda 1, 1, eta 1, 1, plus lambda 2, 1, lambda 2, 1, eta 2, 2. And of course, what is lambda 3, 1?
Also 0.
It's also 0, so we don't care. So we can say 0 plus that plus a 0. The zeros we don't care. So what is lambda 1, 1?
It's 1.
No. What is lambda 1, 1?
Oh,
Cosine theta.
Cosine theta, right? This is cosine theta, right? So we have lambda 1, 1 is cosine theta squared. What is eta 1, 1?
1.
1. So cosine squared theta. What is lambda 2, 1?
Sine theta.
Sine, well, minus, yeah, but it's so squared. So we have plus sine squared theta, and eta 2, 2 is 1. So we got the identity. Cosine squared theta plus sine squared theta is equal to 1. Now you can do that, check that for any, this was for one of the 16 equations, right? We said there are a total of 16 equations here. We only checked one of them. You can go and check the other 15. Okay? And you find out that they are all being fulfilled. And since all the 16 equations are fulfilled, then I say that the rotations are legitimate Lorentz transformation.
Can we find if some transformation is valid without checking all the equations?
In principle, no, but practically there are not that many, so we're simply going to go over all of them. Right, so I mean, practically we're going to go over all possible Lorentz transformations now. So one thing is rotations, right? We said, okay, the first thing we said there is a translation, which is called, right, which is a simple shift of the origin.
Asaf?
Just a second, I finish answer and then you answer.
Sorry.
So we have a translation, then we say the second type is called rotations. Maybe it should be a 2, right? This is rotations. And then there is a third type. There are actually 4 and 5, but I'm going to get to that. So practically, we're going to go through the entire set of them. Yes, now there was another question.
You can say that every unitary transformation is legitimate, no? Is a Lorentz transformation, no? Because of if you
Mhm.
raise both sides by power of 2, the left side is always 1.
No, because eta is not changed.
Eta is not changed.
Yes, eta is fixed matrix. I didn't touch eta.
Okay.
Okay.
There's one thing I'm confused by. How do we know when to use superscript to subscripts for mainly the Mikowski?
We'll get to that. Right now, when we speak about position, it's always going to be a superscript. Always. Okay. We will thoroughly discuss that because this is indeed crucially important. Right now, we only define vectors. Actually, we only define the position for vector, location for vector. That's the only vector that we define. And then we define the matrix, the metric, which has 2 lower indices, and then we define the Lorentz transformation with 1 upper and 1 lower index, such that we can make use of the Einstein summation convention. So it transforms from one vector to another vector, one coordinate vector to another coordinate vector, right? Like here. And just erase the space. Ah, what did it? Right? So far, the only thing I defined is the position for vector, x mu, the metric with 2 lower indices, and Lorentz transformation with 1 upper and 1 lower index. That's all. Of course, we're going to define many more vectors and other quantities, but right now that's the only ones that we define. But we'll wait with the other definitions until next week. Okay. So the third group of transformation, these are called boosts. And the simple way of thinking of them is simply rotation between one of the space coordinates and the time direction. So rotations between space and time direction. So the mathematical structure, in fact, is the same as rotations. Of course, there is a slight difference, right? First, I didn't put it right. Obviously, theta is between 0 and 2 pi. So the boost, as an example, we consider the boost rotation in the t and x coordinates. Of course, the difference is that the time comes with a minus sign. That requires us with a slight different way of writing. So instead of writing cosine sine, then we switch to cosine hyperbolicus and sinus hyperbolicus, and we add up 1 minus sine. So the rotation between time and space is written as cosine hyperbolicus of phi minus sine hyperbolicus of phi minus sine hyperbolicus of phi cosine hyperbolicus of phi. 0, 0, 0, 0, 0, 0, 0, 0, and that is a 1, 0, 0, 1. So this is a rotation. Looks nearly the same, right? Only the cosine hyperbolicus is because of the minus sign that we have. It's very similar to rotation, but written with the cosine hyperbolicus. And there is an extra minus sign. If you look carefully, you see that here there was only one minus sign here, and here we had two minuses. Of course, while theta was limited between 0 and 2 pi, phi, the cosine hyperbolicus and sine hyperbolicus, as you know, you can get them any value, so phi is not limited. So phi is between minus infinity to plus infinity. Now again, we can make direct substitution and prove that this is indeed a valid Lorentz transformation. So for example, again, you need to do the 16 tests, which I'm not going to do, but of course you're very welcome to do that in between the alarms. So example, e.g., right, again, we select rho equal 1, sigma equal to 1. Then we get eta 1, 1, which is 1. And lambda mu prime 1, lambda mu prime 1, eta mu prime mu prime. So which one is not 0? What would be the only non-zero components here? Of course, we have total here 16 components, but most of them are going to be 0, either by the first, of course, every component in which eta prime is different than u prime is 0 because of the eta. And also, so that leaves us, out of 16, we have only 4. 12, we already know that they're 0. And out of these 4, which ones are not 0? Come on, you can speak up.
Lambda 0, the diagonal one.
Well, you said only those with mu prime equal to nu prime, right? So the only non-zero is lambda. What about lambda 0, 1? Is it 0? What is lambda 0, 1?
Minus sinus hyperbolic. Right? Right?
That's true. So this is not 0. So we have lambda 0, 1, lambda 0, 1, eta 0, 0. Plus, what about lambda 1, 1? Is it 0?
Hyperbolic cosine.
Is it cosine, right? So we have eta 1, 1. What about lambda 1, lambda 2, 1?
0.
0, right? Lambda 2, 1 is 0, so I don't bother writing it. What about lambda 3, 1?
Also 0.
0.
Also 0, right? Right, plus lambda 2, 1, lambda 2, 1, eta 2, 2, plus lambda 3, 1, lambda 3, 1, eta 3, 3. This is 0, this is 0, so I don't care. So I have, what is eta 0, 0?
Minus 1.
Right, so we have a minus sign hyperbolicus squared phi. What is eta 1, 1?
Plus 1.
Plus 1. So we have a plus cosine hyperbolicus squared phi. What is cosine hyperbolicus square phi minus sine hyperbolicus square phi?
1.
1, which is what we have here. So this is one component. You need to go through 16 components and check out that the equations, 16 equations are fulfilled. And you'll see that indeed they are, which means that this is a legitimate Lorentz transformation. Okay, so you can complete the proof. It's gonna be a little bit more lengthy, but you know, if you're getting confused, and I do have a very strong feeling based on the fact that you are just looking at me, and most of you are not saying anything, then I have a strong feeling that you may be confused. And I'm not blaming you because this is confusing, seeing this thing for the first time. I do urge you to go and do these things at home. Don't say, okay, we'll get it later, because later it's going to get much more complicated. So right now, make sure I'm very serious about it. Make sure that you fully understand what I'm saying. Okay? It's not the course that you're waiting until later to make sure that you understand. You have to understand it now, because if you don't understand it now, I'm told you, by Passover you will be out of this course because you will get no clue what I'm talking about.
I have a question.
Yes.
So I'm having a lot of trouble bridging this with the more classical Lorentz transformation of 1 over the square root of 1 minus blah blah blah.
Good. So let's do it now. That's exactly what I'm going to do now. Just before, this is a Lorentz. First of all, this is Lorentz transformation. I'm not cheating. Now, the other things that we have, which I'm not going to talk about, other legitimate Lorentz transformation are called discrete transformations. So we have time reversal or reversal of space. We're not going to deal with those in this course. So others, right? Discrete transformation. Time or space reversal. These are legitimate because they fill the same condition that I wrote. Another thing, of course, is a combination. So multiplying one Lorentz transformation with another Lorentz transformation, for example, transformation, boost in the tx direction and then rotation around the x-axis or something. This is also going to give you, but that's going to be very complicated. We don't need that. Two Lorentz transformations in general do not commute. So it's very similar to rotations, right? Rotations, for example, do not commute. Is there anybody who's not familiar with that concept? Rotations do not commute, right? If I'm having, this is my, right. Let's define axis X, Y, and Z. So if I'm making a rotation around the X-axis and then around the Z-axis, I get 1, right? I'm going back, I'm making a rotation around the Z-axis and then around the X-axis, I get to a different location in space, which means that the rotations do not commute. Same means that the Lorentz transformations do not commute. If I'm making a Lorentz transformation and a second Lorentz transformation, the order matters. In math lingo, this is called a non-abelian group theory. We're not going to deal with those because we don't really need that, but just that you know. Lorentz transformation. Do not commute in general, right? You have two around the x-axis, they will commute. Do not commute. This is called Lorentz group is non-abelian group. That's the mathematical name for a group that contains elements that do not commute with each other. If we're adding to that the translations, then we get a more general group. This is called a Poincaré group, in case you've heard the name. If not, then leave it. We're not going to use it in this course. Okay. Now, I was asked a very good question. Let's look at this Lorentz transformation, and you are rightfully asking, how does that has anything to do with what we learned about Lorentz transformations in first year? Right, so let's see. So let's take this boost and multiply it with a 4 vector, right? This is a boost from one coordinate system to another, right? So I can take that and multiply that by 4 vector, right? CT, X, Y, Z, right? And this is going to be equal to CT prime, X prime, Y prime, Z prime. Right, so if I do this multiplication, right, what do I get? Well, CT prime is equal, again, CT times cosine hyperbolicus of phi. Right? Minus x times sine hyperbolicus of phi. And x prime is equal minus CT sine hyperbolicus of phi plus x cosine hyperbolicus of phi. Yeah? Yes or no?
Yep.
Yeah?
Oh, it's a rotation of the light cone, no?
So what?
Of the light cone. Is that what's happening?
No, there's no light cone. Don't worry. Wait. I just took the Lorentz transformation, multiplied it by the 4 vector of position of as measured by one observer. This actually should be in red, right? This is the red observer here. The prime. Z prime, Y prime, X prime, C, T prime. Right? I just made a transformation from one coordinate to another. Right now, let's assume that X prime is equal to 0. So at X prime equal to 0, the velocity, right, beta is beta. So I'm putting here this is equal to 0. And the velocity is v over c. So I can write it as x over ct, which is a what? It's a sine hyperbolicus of phi, x over ct, right? Sine hyperbolicus of phi over cosine hyperbolicus of phi. Cosine hyperbolicus of phi, which is nothing but tangent hyperbolicus of phi. Remember, phi goes from minus infinity to plus infinity. That's no problem. All right, now I can use some algebraic identities, which you may or may not remember from your, I don't know, which course you learn about hyperbolic functions? Which course?
None, I think. Like with Vento, I talk like about them in detail in any course. Like we just know they work and when to use them sometimes.
You never learned them? Is there anybody who's not familiar with hyperbolicus functions? Come on, guys. Either you admit...
We never really learned about them rigorously, but we touched upon them in many courses, in modern ideas in physics and in Memphis 3. We use them a lot, but we never really got taught about them.
Okay. Strange, I'll check it out. But right now we're also really using them. We don't need much more than that because what we do need some identities, right? So if you know, maybe you remember, what is 1 minus tangent hyperbolicus squared? Fine. You may or may not remember that. It's 1 over cosine hyperbolicus squared of phi. And of course, sine hyperbolicus squared of phi is cosine hyperbolicus squared of phi minus 1. Right? These are simply identities. So from here we get that cosine hyperbolicus squared of phi is, sorry, without the squared. Let's remove the squared. Cosine hyperbolicus of phi is square was 1 minus tangent hyperbolicus square root of phi minus 1/2. But tangent hyperbolicus we call a beta. So this is 1 minus beta squared minus 1/2. So we call this gamma. And therefore sine hyperbolicus phi is a gamma squared minus 1/2, which is just gamma beta. And this follows directly from these mathematical identities. So using these, every time I have a sine hyperbolicus, I can write a gamma beta. Every time I have a cosine hyperbolicus, I can write a gamma. So overall, I have a CT prime is gamma times CT minus beta x. X prime is gamma x minus beta CT. And voila! That you've seen, for sure. Right?
Yes.
Yes.
Yes. I told you. It's the same thing. I just show you the mathematical structure of how these things really are. And of course, you can generalize them to any direction. So, although everything we did looked very, very abstract and very, very confusing, possibly, not possibly, it is very confusing for the first time that you're seeing these things. At the end of the day, it's the same thing as you already thought. You reached exactly the same result. So now let's do a little bit of physics, and I think this will be a good place to stop. So the little bit of physics is time dilation.
Can I ask a little technical question?
Yes.
In the lambda, the matrix, the subscript and the superscript, what are the meanings?
Well, lambda really is a matrix that converts from one frame to another, right? So in reality, this is how this is how I use lambda, right? I take lambda and I multiply it by the 4 vector representing the location in one frame, and I get a 4 vector representing the location in another frame.
Yes,
right?
but when I look at
So the 4 vector representing the location in this frame, right? This is x nu. The lambda matrix is lambda mu prime nu, and that vector here is x mu prime.
right.
So
And when I look on, for example, lambda 1 0, 1 is the rows or the
it's always you're starting with the number of lines. So this is the first, and this is the second index.
Okay, thanks.
Okay, that's always. I know I got quite confused by that.
Thank you.
Okay, so this is really this equation, and what's written here is the same thing. This is a very compact way. I mean, this is a compact way of writing this, which is also a compact way in a way, right? In a sense. Okay? Good.
Yes, thank you.
No, it's okay. I did not erase too much or something erased. I don't know how to do back. Okay, so let's go down. Physics. Time dilation. It's already what we have is already enough to start doing some physics, although we're going to do on Sunday plenty of more math. But the aim is not the math, not the aim is the physics. Concept of time dilation. Consider an observer which is in frame O at rest. Observer at rest. Me. And I'm holding a clock. Right, I have a clock. I don't know if you can see it, right? I have a clock. Clock is attached to me. What is the velocity of the clock relative to me?
0.
0, right? But so in my frame, I see 2 ticks of the clock. And the nice thing about here is that the ticks can be, doesn't matter which type of clock. This is electronic clock, could be a mechanical clock, could be a cuckoo clock, could be a biological clock of my cells, right? It doesn't matter, right? The clock is not moving relative to me. So in my frame, I have 2 ticks of the clock, 2 ticks of the clock are separated by delta x is delta y is delta z is equal to 0, and delta t is dt, which is what the manufacturer of the clock meant. Right? And this is set by the manufacturer. And it has a name because it's quite important. And that name is, you may have heard. Actually, you have heard.
Proper.
This is called the proper time. And often this is denoted by d tau to denote the proper time. Okay. Now, remember, according to the definition of the interval which we had, d delta tau squared is nothing but minus delta s squared divided by c squared. So I can write it minus 1 over c squared eta mu nu delta x mu delta x nu. Right? Now, let's say right now, obviously I'm sitting next to my computer, but let's say that I'm walking next to you, with respect to you. So you're seeing me moving. Right? So now an observer, second observer, O prime, sees the same clock moving at velocity v. Now, of course, according to your system, right, what you see, then the 2 ticks of the clocks, 2 ticks of the clock are separated by delta t prime. This is a prime frame. And also there is a space difference because the clock is moving. And delta x prime, which is v delta t prime. To be precise, we put a vector here. Now remember, the 2 observers, me and you, we always agree on the interval. Right? So the interval delta tau prime, right, is a what? Is a delta t prime squared minus delta x prime squared divided by c squared to the power 1/2. So v over c is beta. So we have a 1 minus beta squared to the power 1/2 times delta t prime. But delta tau prime is equal to delta tau because we all agree on the interval. And so observer O prime, observer O prime is the clock in motion. It ticking at the period delta t prime, right, is delta tau prime times 1 minus beta squared to the power 1/2. But delta tau prime is just delta tau, and delta tau is equal to delta t. So this is just delta t times 1 minus beta squared to the power, minus 1/2, of course, right? Minus 1/2, which is just gamma times delta t. And remember, this is true for any type of clock, which means that if you are seeing me moving, you will see my clock ticks more slowly. So think of it for a second. This is the origin of all these paradoxes that you've seen, right? The twin paradox, right? If one is going as an astronaut and traveling away fast, then somebody who's on Earth will see his clocks moving, so he will see it getting age more slowly. Of course, by yourself, you cannot, live forever like that. Because if your biological clock says that you will die at the year of 100, you got no way of changing that. You'll still die at the year of 100, the age of 100, right? But if you're moving with respect to others, then for them, it will see that you're aging much slower, which means that, you could live until the year 3000 or whatever. Okay. Do you have any questions?
Yeah. I'm still a little confused with boosting. What I really don't understand is what is being rotated
Coordinates.
mathematically.
Coordinates. It's like here, when you have the matrix, you're talking about the Lorentz transformation. So this is a more familiar, the Lorentz transformation here is a more familiar one. Remember, Lorentz transformation takes you from one coordinate system to another coordinate system.
Mm-hmm.
From one observer to another observer. Each observer defines his or her own coordinate system, which we have here, right? We have two observers. Both of them are in inertial frames, but both of them, each one has the right to define his or her own set of coordinates. Coordinate system.
But why a rotation and not a translation?
You can have a translation if you want to.
Mm-hmm.
It's fine. We said a translation is mere offset of the origin. And I said and it's written here that this is a legitimate Lorentz transformation.
Mm-hmm.
So I said that there are 3 types of Lorentz transformations. It's written here as 1, 2, 3. The first one is translation.
Yeah.
It's a legitimate Lorentz transformation. The second is rotation, which you may not have thought of it as a Lorentz transformation, but it is. And the third is a boost, which mathematically speaking has the same structure of rotation, only that time is one of the axes.
Okay.
And I said there are the fourth one is so this is, sorry, why did I say 2? It's 3. This is a third type of, sorry, this is 2, this is rotations, and then boost is number 3. It's written here, number 3. I did not get confused. I said number 4 are discrete transformations, which we don't care about in this course.
Yeah.
And then you can also mix them, right? You can do one after the other. The only caveat that you have to remember is that these are non-abelian, so the order matters. If you first boost and then rotate, or first rotate and then boost, you're going to get different results. Mathematically speaking, we don't care about this really. We don't need them in this course. So don't worry about that.
Okay.
Okay. Guys, I'm unhappy with the quietness. This is the first class. I know that what we said here might be a little bit confusing, maybe a little bit shocking, I don't know. Definitely assuming this is the first time you've seen it. I mean, those who were in the particle physics course saw, I think, some of that, maybe even all of that. So don't worry. Next on Sunday, you're going to see things we have not talked about in the particle physics course because we didn't have to, but here we do have to. It can be confusing, but it's not that. It's at the end of the day, it's a math, right? This course is going to be on the edge between math and physics. We're going to make sure that I'm going to make sure to get the right balance. So we get the right math, and then you can see what to do with it. I've shown you that this very abstract notation that we got is in fact identical to the Lorentz transformation that you have seen already in modern physics course. I've shown you that it gives you the same physical result of the time dilation that you have seen. It's way more general, likely, than what you've seen. And we need this generality to when we need to move forward to general relativity. But it's the same thing. If it confuses you, go back, look at the special relativity course, that part of the course that you've seen, see that it's exactly the same thing. It's just more general. More questions. I'm unhappy with that you're not asking questions. I want to encourage you to ask questions. You know, Richard Feynman, which I'm sure you've all heard of. It's well known in his book. If you haven't read his book, I definitely recommend that you read it. He speaks about that the students don't ask questions because they fear that they might sound stupid, but they put themselves in a big problem. And
I do have a question,
Yes,
but it's a little off topic.
okay.
So basically, I'm thinking of the twin stud experiment.
Yeah.
So say the observer on Earth sees the twin leave Earth at relativistic speeds. They see the twin aging slowly.
Yeah.
But of course, the twin is still aging at a constant interval that they both agree on. But say if the twin returns, will they be older or will they be the same age?
That's the thing of the paradox, right? What do you think?
I think older.
Yeah, you're right. You'll be older. Why? What breaks the symmetry?
Deceleration and acceleration.
Exactly.
Okay.
Once you're changing from when it accelerates to accelerate, it's no longer a inertial reference frame. Remember everything we said is relevant as long as we speak about inertial reference frames. One of the things we're going to do when we speak about GR is to talk about non-inertial reference frames. That's the whole point.
Okay.
Okay? This indeed
Yeah.
solves this paradox. Maybe I shouldn't have told you that. Maybe I should have let you think of it for yourself a little bit more. In a few weeks' time, you will know the answer when we start speaking about non-inertial frames.
Okay.
Okay. Do you have more questions? I
No.
do urge you again. This is not difficult. It might be new and confusing.
Yes, I have two
Yes,
questions.
please.
One, the main unit system, this course gonna be MKS.
I didn't speak about unit systems here.
Yeah, because
I
in
can
particle
speak.
physics we use the C=1 stuff. So
Yeah, okay. The only thing is that I'm keeping C in the meantime. I will get rid of C at a certain point. C will be equal to 1. I'm keeping C because I feel that it's at this point it's still so confusing. I assume, I don't know, right? I cannot get into your mind. But I assume that it's so confusing. I'm trying to make it as least confusing as possible. At a certain point, of course, C is going to be equal to 1. Right now, I still keep C.
okay, and the second question, how do you recommend to practice for the lectures? Like, should I read something before the lecture? Maybe the last lecture or
If you want to, you can.
something from the
There are
book?
texts. I mean, I gave you the list of textbooks. The syllabus is on the course webpage. This part is, you can find it on special activity on many places. I recommend Sean Carroll textbook.
Yeah, I use this one.
I think it's maybe not the first, maybe the second chapter. I recommend that you go and read it. It's all in there, but of course there are many other textbooks as well, which I mentioned them in the last lecture. So by no means go and I mean I don't know what to tell you, right? All these textbooks are in the library. I'm sure that they are there. I know that I think most of them they are electronic versions, so you can. I'm pretty sure Carl we have an electronic version. I know that they also have real paper versions, but I don't think it's possible to retrieve them right now because the libraries are closed, unfortunately. So yeah, this will be the best things. And of course, go over this lecture. This is recorded, except from the first few minutes that I forgot to record. That was my mistake. Please, I ask you to remind me in the beginning of each lecture. And then, you can look at this again in this lecture. Okay, again, it's not difficult, but it is confusing. Okay, but make
Okay.
sure you don't get confused because Sunday will get more confusing. So make sure that you follow exactly what I said here. Note that I did not. I make sure that everything that I use is defined. I did not make any use of things I did not define. That's crucial. Okay, and all the definitions were set up very clearly, I hope, right? So make sure that you follow exactly what it means, because every index, every notation have a meaning, and you will get gradually familiar with the meaning of everything here.
Yeah. When we use script in which says how do we refer them from powers of, I don't know, something.
That's a good point. When you have superscripts, there are superscripts. Normally, we will see where they are. We will use that, and we don't make powers really here, except from squared or something. But then it should be clear. That's why I put the parentheses. There is a square. But normally, we won't bother writing delta x2. Typically, I'm doing that now just to make you get used to that. But I'll simply write delta x mu, And you will understand that when I say delta x mu, mu goes from 0, 1, 2, 3. So I can write down delta x mu squared, and then you'll know that it's delta x mu squared and not delta x squared. Okay? Normally, I will refer to these components. There will be, I told you, it's a good course to refresh all your Greek knowledge because we're going to make use of pretty much the entire Greek alphabet. Okay. Any further things? So we're going to meet again on Sunday, and I strongly urge you, go over, make sure that everything sits good in your mind here before we're going further, because on Sunday there will be even some more confusing things. So we have to do a little bit more math before we can proceed with the physics. Believe me, I'm giving you the minimum math that is needed to get the physics properly. But yeah, make sure that you follow closely what we have here, because there will be some more math on Sunday. And then we could start to some physics. You'll see, we'll spend a lot of time on the math, and then the physics will come out very, very naturally. There'll be very little to do once we get it sorted out. All right, guys. Okay, so stay safe. Remember, if you're here, then you know that the Zoom is not the same link for Sunday and Thursday. This is not me. This is the technical. There is an official announcement that next week the lectures are going to continue to be held via Zoom. So this is not my decision. This is a university decision. This is true for all the courses that you're taking. I don't have any control of that. If you want to meet with me, then just drop me a line. You know how to reach me. I gave you my email. I can give it again if you need. And then we can set a time to meet, and then I'll come to office and we can meet there. Okay? So hopefully things will come down very quickly and we don't need to go through that again. In the meantime, have a quiet and safe and productive weekend.
Thank you very much.
See you all on Sunday at 10 a.m. See,
Thank
I
you.
don't know if I'll put the homework today or we'll wait for Sunday, so we'll learn a little bit more than you can do with the full homework. All right. Oh, now I can see the chat, by the way. Is there anything else? That's it. All right. So we can end. Where's the recording thing? I don't know.
Thank you.
All right. Thank you. Bye-bye, guys.